All right, so the meeting is now recorded and I think we can start. So let's start. Hello, everyone. Welcome to episode 33 of Warsaw Quantum Computing Group meetup. Today we have a great speaker, Justyna Zawalska, and she will give a talk titled Hybrid Quantum Classical Machine Learning with TensorFlow Quantum. So sounds very interesting. This meeting is recorded as usually, so hopefully the video will be later available on our YouTube channel. If you have any questions during the lecture, please post your questions on our chat. So if there are some technical questions about details that are on the slides, I will ask Justyna, so we'll try to interrupt. But at the end, there will be also a Q&A session. And by default, please keep your microphone turned off if possible.
I know.
Okay. Thank you. So yeah, before we start, I would like to thank our strategic partners for just helping us in organizing this event, SNARTO and COVID. Also, we would like to thank our honorary partners for helping us advertise this event. And yeah, I think that's all. We can start. I can see one message on our chat. Yes, so this is just a request to all of you. So please try to keep your microphone muted. And if you have any question, please first post your question on our chat, and we'll just try to ask this question either during the lecture or during the Q&A session at the end. So I think we can start. I will now stop sharing my slides. Justyna, if you are ready, we can start. So first of all, thank you for accepting our invitation. It's our pleasure to have you here with us. And the Zoom is yours.
Okay, thank you. Can you see my slides?
Yes, at least I can see your slides.
Okay, thank you for confirmation. So in my talk, I will focus on hybrid quantum classical machine learning with TensorFlow Quantum, and I will present the results of my master's thesis research. Quantum machine learning is gaining more and more attention. If we are to explore this area, then we need to have suitable software that will reduce, for example, the engineering effort, and it will also accelerate research. At present, there exist a few software solutions dedicated to hybrid quantum classical machine learning. But the question is, can hybrid models be created the way the classical models are? To answer this question, I will present TensorFlow Quantum, a library for hybrid quantum classical machine learning. This library was released less than 2 years ago. During this time, the original paper that describes this library was cited almost 130 times. So it may seem that this library is gaining a lot of attention. My presentation will consist of 3 parts. The first one will be an outline of TensorFlow Quantum, in which I will describe the architecture and specification of this library. In the second part, I will provide a theoretical background that will be required to understand 2 experiments, and the experiments will be described in the last part of this presentation. Also, the experiments are based on using hybrid quantum classical feed-forward neural networks to solve the traveling salesman problem, and I will introduce them in the last section. So let's begin with the outline of TensorFlow Quantum. TensorFlow Quantum is a framework for quantum machine learning. It allows creating machine learning models for both classical and quantum data. To enable this hybrid approach, this library bridges the capabilities of 2 other Google products, TensorFlow, which is one of the most popular machine learning libraries for classical data, and Cirq, which is used for programming quantum circuits. In fact, TensorFlow Quantum just implements the missing components needed to connect TensorFlow with quantum information. For example, it provides definitions of quantum layers and implementations of hybrid quantum classical automatic differentiation schemes. TensorFlow Quantum is an open source Python framework developed by Google. Its architecture by design enables interleaving interactions between components of TensorFlow Quantum with components of TensorFlow. TensorFlow Quantum is backend agnostic. Apart from using simulators, it also can be used with quantum devices. Access to some of the quantum hardware like Google's or Pascal's QPUs is restricted only to selected partners, but access to other QPUs like from IonQ or Rigetti is available via a paid subscription. TensorFlow Quantum and the other most popular libraries that support quantum machine learning, such as PennyLane and Qiskit, have many similarities. All of them use Python, are open source, and have integrated some external machine learning tools. By design, they should be compatible with many gate-based quantum computing backends. When it comes to Qiskit's machine learning module, it has been introduced very recently. So because of that, compared to other libraries, it provides the fewest number of available tutorials and implementations of research papers. Let me move on to introducing the theoretical background that will be necessary to understand the experiments from the next section. First of all, I will briefly explain how the hybrid quantum classical algorithms work. Then I will introduce one of these types of algorithms, the quantum approximate optimization algorithm. At the end, I will describe the design of hybrid quantum classical feed-forward neural networks. Current quantum computers are considered noisy intermediate scale quantum devices. On the one hand, these devices cannot perform very challenging tasks. But on the other, they are well suited for performing hybrid quantum classical algorithms. Basically, hybrid computation consists of tasks that can be split into classical and quantum subroutines. These subroutines are executed in a loop on different devices. This technique is based on the fact that the longer the quantum computation, the higher the error rate. So the idea is that the circuit on a quantum computer should be short and controlled by a classical computer that adjusts this quantum circuit in a loop. Currently, one of the most important hybrid algorithms is the quantum approximate optimization algorithm, QAOA. QAOA is mainly used to solve combinatorial optimization problems. So the problems in which the search space is discrete and too large to be fully searched. First of all, we need to obtain the cost operator, which depends on the optimization objective. So the classical cost function acting on binary strings should be translated into the cost Hamiltonian acting on qubits. Then we need to have a mixing operator. The simplest mixing operator is the sum of Pauli X gates. This operator preserves the feasible solution space and provides transitions between configurations that belong to this solution subspace. When we have both of the operators, we can define the cost and mixer layers. These layers can be expressed in the form of a parametrized quantum circuit. So the parametrized quantum circuit usually describes a subroutine consisting of a sequence of gates applied to specific wires. It only defines the base structure, and the types of the gates and their free parameters can be optimized with an optimization procedure. So having all that, we need to choose a parameter P that will define the depth of the circuit ansatz. What is characteristic is that the circuit ansatz is based on two layers, coast and mixer layers applied in alternation. The parameters of the quantum circuit are adjusted by the classical optimizer to return the smallest possible value for the quantum measurement. This value should approximate the minimum of the cost function. I will provide more details on how to use and implement this algorithm in the next part of my presentation. But what is important is that we can control the depth P of the circuit ansatz. Now let's focus on the hybrid feed-forward neural networks that are the backbone of my experiments. The classical feed-forward neural networks are a type of neural networks in which the neurons from one layer are only connected with the neurons from the next layer. And we have an input layer, one or many hidden layers, and an output layer. In the hybrid case, the design is very similar. The main difference is that a classical layer can be replaced with a quantum layer, typically a parametrized quantum circuit layer. A quantum layer as input receives classical values. These values can be applied to the parametrized quantum circuit. Then the quantum circuit is measured and the measurement results, so also a classical value, is the output of this layer.
Okay. Justyna, it looks that there is a question, so at least I can see that Ashmit has raised his hand. Ashmit, would you like to ask something regarding the current slides? You can unmute yourself for a while.
Will we get PDF of this?
Could you please repeat?
Will we get PDF of these PPT?
The slides, right? PDF slides?
Yes, yes.
I think I can send you the slides. Yeah, okay, no problem.
Okay, thanks.
Thank you.
Okay, so let's move on to the next slide. How are the hybrid quantum classical neural networks trained? The training consists of constant adjustments of both quantum and classical parameters. One of the crucial steps is training the hybrid quantum classical neural network is evaluating the loss function. When we calculate the loss function, we can determine its gradients for both classical and quantum parameters. And then the parameters can be updated. Now let's move on to the experiments. I will present two experiments showing how to use this library to solve the traveling salesman problem with quantum classical feed-forward neural networks using QAOA. The first experiment will examine the possibility of minimizing the expectation value for a single traveling salesman problem instance. The second experiment will investigate the generalization abilities of a hybrid quantum classical neural network trained with many instances of the traveling salesman problem. And also I will show how to implement this first experiment. So for the purpose of using the hybrid feed-forward neural network with the QAOA, I chose the traveling salesman problem. It's an NP-hard combinatorial optimization problem. In this problem, we need to find a path to a weighted graph that starts and ends at the same vertex, includes every other vertex exactly once, and minimizes the total cost of edges. The first step was to create a single instance of the traveling salesman problem. Since the algorithm was executed on a quantum simulator, a feasible example to solve consisted of 4 cities, so it was 16 qubits. From the perspective of optimizing the loss function, it was beneficial to limit the range of distances between cities, so the city coordinates were normalized. The matrix of distances between cities was determined as the Euclidean distance between the normalized city coordinates. To convert the integer representation of the city identifiers to binary representation, I selected one-hot encoding. One-hot encoding is a type of vector representation in which all of the elements in a vector are 0, except for a single one that represents a specified feature.
I have one question, if I can ask. So you mentioned that you needed 16 qubits for cities. How does it scale with the number of cities? Is it always an n square or?
Yeah.
Okay.
Because of this one-hot encoding, it's always n squared.
Okay, good. Thanks.
Thank you. To solve TSP with the QAOA, it is necessary to encode this problem formulation into a cost Hamiltonian. And usually it is helpful to start with defining the quadratic unconstrained binary optimization formulation of the problem and then translate it into the Hamiltonian. So we define the binary variable XIT, and it is 1 if the salesman visits the city I at the timestamp t, otherwise it's 0. We have the cost function b that expresses the sum of costs for each taken path. And also we have constraints A1 and A2, and they ensure the solution's correctness. So if the solution is incorrect, a suitable penalty is added. And generally the task is to minimize the weighted sum of this cost function and constraints, and this function is Cuba C. But that was Cuba formulation, and we need to have a cost Hamiltonian. So when we have this Cuba form, it's easy to obtain the Hamiltonian. We only need to substitute all x's with the proper sum of Pauli operators. And the Hamiltonians can be translated into the cost and mixer layers of the QAOA ansatz. And now I will show you the first experiment. The first experiment examined the possibility of minimizing the expectation value for a single traveling salesman problem instance with the use of a quantum feed-forward neural network. I proposed a hybrid network that consisted of an input layer with 2 P neurons, and P is the number of parameters in the QAOA circuit. And this P also corresponds to the depth of the circuit. Also, this network consisted of a hidden layer with 2 P neurons and an expectation layer that outputs classical information based on the measurement of a quantum state. The design of this network was based on the fact that the input, so the initial values gamma and beta, had 2 P parameters, and the expectation layer also needed to receive 2 P parameters. And the intermediate layer, this hidden layer, was used to increase the network's capacity. The results of this experiment show that with the increasing number of the variational layers, the loss function decreases and the percent of correct solution increases. And this is in accordance with the theoretical considerations. So in general, the bigger the P, the better results we get. And when we take a look on the graphs representing the training loss for the for optimizing quantum neural network with P p equal to 10, we can observe that the attempt to minimize the expectation value was successful, since the value dropped from above 70 to around 3.6.
May I have a question regarding this optimal solution? If you can go back. So this is a correct solution and it's a percentage of the correct solution. So how to interpret that? Let's say it's 92.5% of the correct solution. So because in the TSP, traveling salesman problem, we have, so we are looking for the path that would have the minimal cost, let's say, right? So how to interpret that this is, let's say 92% of the correct solution?
So the quantum circuit with the proper angles was sampled to the 16, to the power of 16 times. And then I calculated how many correct solutions are there, and that's the percentage of correct solutions from these samples.
From the large number of repetitions. All right, great.
Yeah.
Cool, thank you.
Thank you. Also, I will show how I calculate this in this part when I will show the implementation, so that will become more clear then, I hope. And okay, so here I wrote that the circuit was sampled to the 16 times. And what's interesting is that the number of occurrences is very different from the last correct solution, and it's a big difference. Like there is a significant gap between the number of occurrences of correct and incorrect solutions. And I also distinguish correct solutions and optimal solutions. So the optimal solution is like the best solution, but the correct solution is the solution in which we preserve this one hot encoding. So it's not the best solution, but the encoding is correct. And I will now describe the second experiment. The aim of the second experiment was to explore the generalization abilities of a hybrid neural network. I investigated whether it's possible to obtain a hybrid quantum classical feed-forward neural network, and that after training on many instances of the traveling salesman problem will yield proper angles gamma and beta for an unseen instance of the TSP. When it comes to the neural network model, it consisted of 5 layers, an input layer with 2p neurons, 2 hidden layers with 32 neurons each, a hidden layer with 2p neurons, and an expectation layer to prevent the problem of overfitting, which means performing very well on training data and poorly on testing data. I used the regularization technique called dropout. In the hidden layers, I used a nonlinear activation function, and this activation function just specifies the way of transforming neuron inputs into an output. And also the data set I used was divided into the training data that consisted of 800 sets of distances, the test data 100 sets of distances, and the validation data also 100 sets of distances. The training data was used, of course, for training the network. The validation data was used for diagnosing the learning performance during training, and the test data was used for evaluating the model after training. So the training loss value estimates the expectation value of the training data, and the test loss value estimates the expectation value on the training data. Both of the losses are of similar value, so it means that the network performed well on new data. The last column represents the percent of correct solutions for a selected new test case with the same CET coordinates as in the first experiment. similarly to the results from the previous experiment, it can be noticed that the greater the value of P, the lower the training loss and the higher the number of correct solutions.
Justyna, there are two more questions on our chat, so maybe let me ask if we can ask
sure.
now. Okay, right. So one question is from Itamar. So there was the number 1,741 unique solutions, right? 1741. So I think it's a question whether we can interpret it as a number of unique solutions. I guess. I think it was maybe probably 2 slides earlier. Yes.
Yeah.
Oh, here.
Yes. So I sampled the circuit almost like above 65,000 times. So there are more than 65,000 possible solutions. But out of this space of 65,000 possible solutions, only 1,741 solutions were found. So there are 65,000 combinations of zeros and ones in this 16-bit bit string, but I only sampled almost 2,000 of them. Like there wasn't some of the possible sample strings in the result I got.
And many of them were just not correct, right? As we can see at the end.
Yeah.
So some constraints were violated, right? So
yeah, there are only 24 correct, but the algorithm found almost 2,000 solutions.
Okay, there is another question from Yash, so maybe I will also ask at the same time. Is it right that more the number of constraints, the error would increase? So if you have more constraints, then the error would increase.
It depends on the type of the constraint, but if I think yes, because here the constraints are used to force the solution to be one hot encoded. And if we hadn't had this type of constraint, then probably like there would be like many more correct solutions, let's say. So if we have like the constraints cause that so many of the solutions are incorrect. Yeah.
Okay.
I don't know if this answers this question, but I hope so.
I think that yes. So there was just a follow-up comment from Yash that he mostly had time constraints in mind. So specifically time constraints. So I guess that like time windows, for example, in case of TSP, because there are also variants like TSP with time windows. So in general, so my experience is similar as Justyna described. So in general, the more constraints you have, the more difficult it is to obtain good solutions. But as Justyna said, it may also depend on the constraints and also on the type of error that you have in mind, because we can also consider different errors. So for example, here we mostly consider what's the percentage of the correct solutions that are returned. But I guess, and probably Justyna will also confirm it, that when we have, or if we have more locations to visit, then in most cases it might be even difficult to find the correct solution, right, or the optimal solution. So in such case, we may also consider what's the difference between the solution that is found and the optimal solution. So these are some other types of errors as well.
Yeah, that's true. Okay. Also, the traveling salesman problem has the constraints of traveling salesman problem. Like they include, let's say, equality. So let me get back to the proper slide. Like here, we just expected these constraints to be equal to 0. But some of the problems have the constraints with inequalities, and then these examples with constraints with inequalities are much more harder to solve because then we need to use some other techniques like slug variables, and then it can get, let's say, messy because it's not so easy to implement that.
Okay. There's one more question from Itamar. It's also, I think, related to the essence of your talk. So let me just ask it. So how loss value is calculated? I think that there was information about the loss at some point.
Could you repeat the question, please?
How do you calculate? So how is, maybe let's start from definition of the loss function. So we have this definition here on the slide. So Itamar, I'm not sure if it already answers your questions, or I guess that there's a question how it's calculated. So maybe I'm not sure if you can maybe also elaborate.
Talking about numbers, not expression. How I get to those numbers around 3?
Okay, yeah, sure.
Best case for the optimal.
Okay, so the loss function is defined as the value from the expectation layer. So as I've said, we had to the 16 samples, like we sampled the circuit that many times. And so first of all, we need to, so what is measured? Measured is this quantum circuit, and we provide here some value of angles. And then when we have these angles, at the end, we measure the expectation value of this whole circuit. So we just like calculate the averages, and maybe I will try to explain it here. So we sample this type of string. Then we use this sampled string like as an input to cost function, classical cost function, and this string will like yield something close to, I don't know, maybe 3. And I do this for all of the sampled strings, and then I calculate the average. So these samples that are like correct and most of all optimal, then they will yield like small values. So when we pass this string 0, 0, 1, 0, etc. to let me find it, to this cost function, it will return a small value, like something close to 2.5 or 3. And when we sample a very incorrect solution, so one of the worst possible solutions will be all ones, then we will also calculate the classical value. So we substitute the x's with ones, and then this value will be kind of big, and then we calculate the average of all these substitutions, and that's the expectation value.
Okay, yeah, clear. Thank you.
Okay, cool. Okay, so
I think we can go on. There are no more questions currently on our chat.
Okay, so I think I talked about that. Okay, so now I will just compare the results, because I conducted 2 experiments. So what's the difference between them? So first of all, the experiments then demonstrated that TensorFlow Quantum can be successfully used for minimizing the cost function of a parameterized quantum circuit for a combinatorial optimization problem. Furthermore, the results of both experiments, when tested on the same problem instance, yield similar results. So there aren't like big differences between the results. However, the advantage is that the network from the generalization experiment, so the second experiment, is strange. So we immediately get a result for new data. And in the first experiment, we just need to train it all, like for new data instance, and we need to train it all over again. So that's it. And now I will want to show you the implementation of the first algorithm. So yeah, I will show you the code. So we need to import all three libraries, TensorFlow and TensorFlow Quantum, because like the all of them are needed. It's not it's not like TensorFlow Quantum has all of their capabilities. They are just supplementing each other. So this code is not that much important, but I've just randomly chosen 4 set of city coordinates. They're from the range from 0 to 10,000. And what I did, I just calculated the distance matrix because this matrix will be used in calculating the cost function. Yeah, and I previously mentioned the distance matrix is just a it's just calculated as an Euclidean distance. Okay, and now we have a little bit more interesting part. So how to implement this QAOA. So first of all, we need to have defined the cost function, and like it's convenient to look at the Cuba formulation of the cost function. So we have just binary variables x, and we need to we have defined the cost function b, the constraints, so we know how the total cost function looks like, and so how to implement it. First of all, like these expressions with sum can just be implemented using the for loop, for example. So so all of these cost functions can be like simply created with we just simply translate the mathematical formula into the code. Like there is nothing like super interesting here. But what's interesting is that we don't need we need Cuba, but it's not the thing that can be passed to the quantum circuit. So we need to have Hamiltonian of this cost function, and to create this Hamiltonian, we need to be able to translate x's into some Pauli gates. So I've mentioned previously, let me find it. Well, here, okay. That x can be seen like it's a Pauli. So it's identity gate minus z divided by 2, and that's just implemented here. So it's really easy. We just need to define x, like instead of a binary variable, it's defined as a Pauli string. Okay.
There's, I can see that Bill has raised his hand. So Bill, would you like to ask a question?
Yes, it's mainly along logistics. Did you have any problems with the different versions of TensorFlow and TensorFlow Quantum? I find that I have to match certain versions when running these particular pieces together, and I didn't know. It looks like you just might have installed just the standard, but I was just curious. And then if anything, just on any time frames, as long as in regards to how long some of these executions might have taken based on your fitting or your training, etc. Okay. That's all.
Thank you for the questions. I will answer the first of them. So the answer to the first question is, yeah, I did have some problems, and I just found the versions that work together nicely, and I just stick to them. So yeah, it happens to me that I think that I've updated either Circ or TensorFlow, and then everything stops to work. So yeah, I know this issue. And the other question was how long? So and this experiment with just using the neural network as an optimizer. So it's exactly this experiment. It takes just seconds, not seconds. Like let me see how much time it takes. It's okay. So it's 2 minutes to train. So it's like not a long time, but I'm using a supercomputer right now. So it's a supercomputer from Academic Computer Center Cybernet. But I can like easily run it on my own PC, and it will be not much more, maybe 3 minutes. So it's not necessary to use a supercomputer to train this type of network. But when I was running the experiment with this more complicated neural network, like bigger neural network, and especially as it consisted like many data inputs, it took on a supercomputer, I think, around 6 hours to train. So the difference in the time is like really big. So does this answer your questions?
Yes, thank you very much.
Thank you. Okay, so I've just described how to transfer these mathematical formulas into a Hamiltonian formulation. Also, what we need to have is a parametrized quantum circuit. Especially, we need to have the circuit ansatz that is from the QAOA algorithm. So we need to create something like the thing that is presented on the picture. So first of all, we need to create a layer of Hadamard gates. So I think it's okay. So it's like pretty easy. We just apply the H gate on proper qubits. So we apply, like basically we apply the H gate for all qubits. And then we need to create the cost operator and mixing operator. I will come back to this slide with the QAOA. Okay, it's here. So we need to have this cost operator and mixing operator to create the layers of our circuit, because basically these layers can be just translated into quantum gates, and that's all we need. So the cost operator is calculated from this formula, and we just need to use proper x's. So it's not, x's are not binary values, but they are just operations on qubits. And yeah, so that's for the cost operator. And for the mixing operator, we just use like a default mixer. So the default mixer is just using Pauli X gate on each qubit, and that's being done here. So we just apply the X qubit on every wire, the X gate on every wire. Sorry. And then the nice thing is what TensorFlow Quantum does. It calculates the exponential function, because here we need to have this cost operator HC or mixing operator HM. Like it's an exponent here, so we need to calculate this value, and we have the tools that help us with this. So we just need to use this function TFQ util exponential, and it will exponentiate this function for us. But there are two things. The first one is that this quantum circuit will can have like user-defined circuit depth. So we define whether it's P equal to 1, so that that will be just one layer of like this cost layer and one mixer layer. But of course we may want to have more layers, because the more layers, the better the result usually. We just need to define this value of P, and then we just can have like this like I don't know, this list of cost operators and mixing operators like in alternation. And also what is important is that these layers are parameterized, so we don't know like exactly what is the value here. We just want to be able to substitute all of these gammas and betas. So we use symbolic operators. In our case, those are the SumPy symbols. So we just create two P parameters, because if we have P equal to 1, then we need gamma 1 and beta 1. So that's 2 parameters. If we have like K parameters, we need to have 2 K parameters. Okay. And that's basically how it works. So this Hadamard circuit will create the layer of Hadamards. Parameterized quantum circuit layers will be created. So these layers, like from gamma 1 to beta P, will be created using this TFQ util exponential. And all we need to do is just to add these layers to have a nice parameterized quantum circuit. So that was the first part, in which we create the circuit that has some parameters that can be optimized. And now I will show how to create a hybrid quantum classical feed-forward neural network. So if some of you are familiar with TensorFlow, like the API is exactly the same. So the first two layers are classical layers. So what we do, we just defined TensorFlow Keras input layer, and this input layer has 2P parameters, and is defined here. The second layer is also a classical layer. So and it's a dense layer, so we can just use like classical Keras dense layer. And the only thing that is new here is the expectation layer. So this expectation layer, I will in a second just say what it does, but that's the quantum layer. So that's the functionality that is being provided by TensorFlow Quantum. So to use this quantum neural network, we need to have in our case, QAOA circuit, and this circuit will be parameterized. So there are some parameters to train, which is good. We also need to have cost operator, which basically is it's another convention, like another naming for cost Hamiltonian. And also we need to have initial parameter values, and that can be tricky. But in my case of this traveling salesman problem, I was using the input vector of all zeros. And the issue is that it's not easy to determine what the input values should be. Like for me, zeros worked, but it's not clear how to choose the initial input values. So these initial parameter values are in okay. So what happens now? We have the initial parameter values, so they are in this input layer, and yeah, and these parameters from the input layer and are then passed to the hidden layer. So it's being done here, and the outputs from the hidden layer is then passed to the expectation layer. So we have two p-values from here because there are 2p neurons, and we need 2p values in this parameterized quantum circuit because there are 2p angles, gamma, beta, to optimize. And those are just some TensorFlow things. So we just need to define the shape of Keras input, TensorFlow Keras input. So it's nothing like super important here. Like the only thing that is important is that the params input will have the size of 2p. Okay, and so the TensorFlow as input takes quantum circuit, takes the Hamiltonian operator and some initial parameters. So in our case, it's all zeros, and as output returns two things. The first one is an array of 2p parameters. So at first we have all zeros, but then we want to know how they were optimized to be like a better solution for our problem. And the second output is an expectation value. So it's calculated on this layer. And then those are just some technicalities. So I just used the Adam optimizer for the optimization routine, and as the loss, I've used mean absolute error, and that's okay. So that is not super important. Okay, and here will be some other important things. So what TensorFlow Quantum brought to TensorFlow is that quantum circuits and cost operators, which are Hamiltonian operators, can be converted to TensorFlow tensors. So then it will be like really easy to calculate some like do back propagation on them and like basically calculate gradients if we use gradient based optimization methods. And in the training part of this model, like as input, I just provide the circuit tensor and this Hamiltonian tensor and initial params. As the output, it's not super important what's in the first output, because those will be just the parameter values. But the important thing here is that we want to minimize the loss function, so the expectation value, and the ideal value is around 2.5. But in general, like the closer the result to zero, the better. So we can just define that this ideal value is 0, because then it will decrease to 0. And after the training, it took like 2 minutes here. I can have I can plot the results, and okay, it shows that the network trained well. And here I don't have like any test data because I'm just optimizing the same circuit. So I won't do here like any tests, but I will just predict the values for this single instance of this traveling salesman problem. So what this neural network returned are the following parameter values. So it's a like a vector of 20 parameters, because I forgot to mention that this QAOA like a circuit was created with p equal to 10. So I will have 20 parameters. So what happens with these parameter values? Like I took this first parameter value, and then it's being supplied to the gates in the first layer of the QAOA. So this will be like gamma 1. Then I take this value, and this value will be supplied here, and it will be beta 1, and so on. So I have these parameter values. So I have two things. I have a parameterized quantum circuit and parameter values that I can use. So what I would like to do now is to use these parameters like as the values of my parameterized quantum circuit. And what TensorFlow Quantum does, it just enables us to use like a simple layer called sample, because I think it's a nice feature, because in Circ, like the in Circ, so the other component from Google for calculating like things on quantum circuits, it will be like a much longer code. So what we just need to do here is to have a layer that we like sample layer. We have the names of the parameters. So the like it's not super important, but okay. So what we do is just we provide to this sample layer the circuit tensor. So it's the parameterized quantum circuit in the form of a tensor. We define the how are the parameters named in this quantum circuit, because we need to know what is being supplied with what. And we have symbol values, and these symbol values are taken from here. So and we define how many times we want to sample the circuit. So after this this sample layer, I can know how this training go. And so here, and that relates to the one of the questions I got. So I have these parameter values. I use them in the quantum circuit, and then there are some probabilities of getting some results. So when I sampled this circuit that many times to the 16, I got around 92% of correct solutions. So yeah, so it means that like this is one of the correct and optimal solutions. So at first we are in the second city, then we go to the third city, then to the first city. Okay, so it starts from 0, so it's 0, 1, 2. Okay, no, it starts from 1. So at first we are in the third city, then we go to the fourth city, then we are in the first city, and then we are in the second city, and we come back to the third city. So it's like a full cycle, but if I know where I started, I don't need to have this this last the last element of this cycle, because it will just waste qubits. So basically that's all. So what we can see here is just like the most common results are the optimal results. So optimal for me means like, not for me, but in general, optimal means that this solution is not only correct, but it's the best solution that we can have. And the correct solution is the solution in which we have correct one-hot encoding. So so we have only just one in a single timestamp. For example, this won't work because in the third timestamp we don't visit any cities. Okay, so that's all for the tutorial. I don't know, are there any questions on the chat?
Yes, there are some questions. So first of all, thank you, Justyna. It was a great presentation, and on our chat we also have some acknowledgements that indeed it was a great presentation and great topic. So we have, I can see at least two questions. So the first question from Emil. What encoding is used to convert the classical values from the hidden classical layer to the quantum layer?
From the hidden layer to
the quantum layer.
So we don't have any type of encoding here. I just use one hidden layer, so I don't use any activation function, because in my case it didn't change anything, and the values here are classical, and they are like this 0 point. Let me see here. It's like the values that are being passed to the expectation layer are just those values. Okay,
so in fact, this is this let's say expectation layer, as you said. So it's already our loss function, so in fact there's no quantum layer just behind this classical.
Yeah, that's true.
All right.
So it's like classical data in and classical data out.
Okay.
From this expectation layer.
All right. So Emil, I hope that it answers your question, but if you have some follow-up questions, then feel free to ask as well. There's another question from Atharva. I think that it should be formulated that what's the advantage of using hybrid quantum neural network with QAOA ansatz over directly solving TSP using QAOA?
Okay, that's an interesting question. So for now, I'd say there is like, okay, how to say it? Like we have better classical algorithms to solve TSP with 4 cities. It's for sure we can use some classical algorithms, and the results will be better. But like I did this experiment just to research the current quantum hybrid quantum classical algorithms. So there is no quantum supremacy with this like right now with these experiments I showed. But the hope is that in the future, when we'll be able to better like obtain better results with quantum computer, then we will be ready to implement some meaningful algorithms. So yeah, that's all.
Okay, good. Atharva, I hope that it answers your question, but if you have any follow-up questions, then feel free to ask. Yeah, so Emil just replied that he will double check the documentation of TensorFlow Quantum. All right. So there's also a message from Itamar regarding ansatz. So Itamar, would you like to maybe ask a question?
Yes, I'd like to elaborate. Okay. First of all, I want to congratulate you on wonderful presentation. If I had a company, you would be hired on the spot, no doubt. I have so much to learn from you. Now, about ansatz, which is not an easy topic, you mentioned it twice in the talk, and I like to know more details about the ansatz. But the question for everybody is, how about, is there room to come with alternative ansatz whenever people are using ansatz to improve the results? And this is not related to this talk only, but to every time that I see ansatz being used.
Well, I've used this QAOA ansatz because I've researched this topic, and I've read that this is a good type of ansatz for combinatorial optimization problems. But like I don't know what type of ansatz should be used for other problems, and I think that there will be, like in the future, there will be many more ansatz that will be suitable for solving some other problems.
Mm-hmm. Have you maybe also investigated or considered some other ansatz?
Like not really, but like okay, instead of QAOA, I could use VQE, but no, I didn't try that.
Okay, good. There's a question from Munavar. Did you use the real quantum computer to obtain the results? So as far as I remember, it was a simulator, right?
Yeah, it was only in the simulator, and in my future work, I will consider that. The issue is that at the time it was June this year, so there weren't any real hardware like available for me. On the 17th of June, IonQ released quantum computer for Circ and TensorFlow Quantum, but it was like too late for me back then. And the other issue is that, okay, so there are two issues. The first of them is that IonQ has only 11 qubits and I needed 16. And the other issue is that running these hybrid quantum classical algorithms can be kind of expensive. So I haven't tested this circuit yet, but I'm like, the thing is that I get like really nice results for p greater, let's say greater than 7, and it's a lot of quantum gates. So unfortunately, I expect that the results on a real quantum hardware won't be as nice as the ones we can see here, because I think that there will be like a lot of error.
Yeah, this is also something that I would expect, that the results will not be as good if you run it on a real quantum computer nowadays, at least. There are also some thanks and acknowledgements for Veselin. So thank you, Vesel. Thank you very much. All right. Do we have any more questions to Justyna? Justyna has a great knowledge on this topic, so it's a last chance to ask a question. Let me just maybe go back, because maybe there were some questions earlier. No, it looks that we've already asked all the questions. So Atharva has a doubt and would like to ask on audio. Yes, sure. Please, Atharva, go on.
Hello.
Yes, we can hear you.
Hi. So first of all, I would like to say it was really wonderful presentation, and thanks a lot for that. So my question was, actually, I'm currently working on VQE. So if I use VQE answers instead of QAOA, so do you think that it will give some better results compared to directly using VQE? So using QNN with VQE, like this approach.
Okay, so I must admit that I haven't tried implementing VQE, but I think the results should be more or less similar. Like, I don't know if there will be like any advantage of using VQE on this type of optimization problem, but yeah, I think that the results should be similar.
Okay, thanks a lot.
Thank you.
All right, do you have any more questions? If not, then I would like to thank once again, first of all, to our great speaker, Justyna. I agree that it was a wonderful presentation. And also I would like to thank our audience for very interesting questions. So I'm happy that there was also a very interesting discussion. Let me maybe share my slides once again at the end, because I would like to announce our next event that will happen most likely on 10th of January. So the speaker will be Antal Shava from Xanadu. So this time, again, it will be quantum machine learning or close to quantum machine learning, but this time using PennyLane. So the title is using PennyLane for quantum differentiable programming. So we'll start advertising this event soon, but probably after the Christmas. So again, we would like to thank our strategic partners, Narto and Cogit, for supporting us, our honorary partners. If you are interested in our events, our meetups, let's stay in touch. So we are welcome to join our Facebook groups, follow our website, our Facebook fan page, YouTube channel, on which we'll hopefully publish the video recording, also the Twitter profile, and so on. And finally, wish you, all of you, happy Christmas. Take care, first of all. Hopefully, it will be a healthy Christmas, and we'll be able to meet again in the next year, in 2022. So let it be a good and successful year for all of us. And I will now stop sharing my slides and stop recording.